In this video, we are going to look at higher ordered non-homogeneous differential equations, and we'll be looking at the method of undetermined coefficients, which is very similar, in fact almost exactly the same as when we did undetermined coefficients for second order differential equations. The form of our differential equations then is a naught y, the nth derivative of y, a1 to the n minus 1 derivative of y, plus all the way down to a n minus 1 y prime plus a n y equals g of t. And what I did not do when we were looking at second order differential equations was use this summary table here. But we will use this now, and this summary table is actually, I should have really explained it when I did second order, but here you go. This is our this is our chance to look at this summary. Although it shouldn't look too foreign to you, because it's very much the techniques we did, as I said, for second order. So the idea of g of t is of the form of a polynomial, an nth degree polynomial. So in other words, it looks like a naught t to the n plus a1 t to the n minus 1 plus all the way down to a to the n. Then our solution, our particular solution, capital Y of t, is going to be equal to the same order of polynomial, a naught t to the n plus a1 t to the n minus 1 plus a n, and these are capital A's because we have to solve for them. And then with the possible addition of this t to the s, and this t to the s, what that means is s is the smallest natural number that ensures that no term in y in our particular solution is a solution to the corresponding homogeneous equation. And we've seen this before, like when we looked at y equals e to the t, if we already had a solution of the form y equals e to the t, what we did is to find a second solution is we just multiplied by a factor of t in front. Same idea here. And we will do examples so you can see examples of that. But anyway, our next possibility is our g of t over here is of the form a polynomial times e to the at. So then we're going to assume our solution is a polynomial, same degree as our polynomial g of t, times e to the alpha t, and we're solving for these coefficients as well as the alpha. Our third possibility is our g of t is equal to a polynomial times e to the at sine of beta t, or the same form of y of t applies for when we have a g of t as a polynomial of n degree n times e to the alpha t cosine of beta t. So both of these have the same form of solution for capital Y of t. It's the polynomial of degree n times e to the at times cosine beta t plus another polynomial of degree n times e to the at sine of beta t. And this again is very similar to what we did for second order differential equations. So we'll do some examples so you can see how all of this works. Our first example is to find the general solution for fourth derivative of y plus 2y double prime plus y is equal to 3 sine of t minus 5 cosine of t. And just like for second order differential equation, the first step is to solve the homogeneous equation. So the homogeneous equation gives us this characteristic equation, r to the fourth plus 2r squared plus 1. And that's equal to r minus I squared and r plus I squared. So this is our general solution. We have yc for the homogeneous equation. The complementary solution is equal to c1 cosine t plus c2 sine t. And now, again, we're going to plug in the t because we can't just, because these two roots are going to have the same form of solution. So we're going to plug in our t here. c3t cosine of t plus c4t sine of t. Now, looking at our table, our g of t is of the form sine and cosine. So what we have here, and there's no polynomial, or polynomial is equal to 1, or I guess you could say polynomial is equal to 3, so we do have a coefficient in front. And then we have no e to the at, but we have sine or cosine. So our solution, again, we're going to have a coefficient, so that's a and b here. No e to the at, but we'll have a cosine of beta t and sine of beta t. And here our beta, there's no, beta is equal to 1. So it's just y is equal to at squared cosine t plus bt squared sine of t. So where did this t squared come from? Well, it came from the fact that if we had just put y equals a cosine of t plus b sine of t, then this solution here would not have been linearly independent to our solutions because of this. It just would have been repeated information from our solution from our homogeneous equation. And it's not sufficient just to put one factor of t in because it would be linearly dependent on this part of the solution. So what we need to do is add this t squared here. Again, that's our t to the s. And s is the smallest natural number that ensures that no term in y, and there are two terms here, our cosine term and our sine term, is a solution to the corresponding homogeneous equation, right? So this is why we have the squared here. So I got rid of my table just so I can make some more room and hopefully maybe have some things a little less cluttered. But this is what we have repeated from our last slide, where we have the solution to our homogeneous equation, and then we have our proposed form of what y should look like, at squared cosine t plus bt squared sine of t. Remember, we put the t squared because y must be linearly independent from the homogeneous equation. Now we can take y prime, we can take y double prime, we can take y triple prime, and I was doing the fourth derivative, except I was complaining bitterly, and then my daughter said, oh, you should use wolframalpha.com, and so I did do that for the fourth derivative. I used wolframalpha.com. But I would encourage doing a few derivatives, even though it's painful. And also, there is a reason to do these by hand, and that is, after a while, the derivatives and how they simplify do follow different patterns. So if you do a lot of them by hand, you'll probably start to notice the pattern, and you will get really quick at it. So you can decide which way you want to do this. Once I have all these derivatives, I can plug in to my original differential equation, which is the fourth derivative plus 2y double prime plus y is equal to 3 sine t minus 5 cosine t. So I just focused on y to the fourth plus 2y double prime plus y. Here's my fourth derivative, my second derivative, and my third derivative. And what ended up happening is a lot of terms ended up canceling out. And after I canceled out these terms, I gathered my sine terms, which I have my minus 12b, and then I have my 4b here. And that's equal to, over here it should be equal to 3 sine of t. So that means, what is this? This is minus 8b should equal to the 3, so b is equal to minus 3/8. I then gathered my cosine terms, and I find that, doing the similar sort of work, I found that a is equal to 5/8. That means my general solution is my complementary solution for my homogeneous equation plus this particular solution, which is 5/8 t squared cosine of t minus 3/8, and then I have where is my general solution? My t squared sine of t. So this is my final solution. Our next example is y triple prime minus 3y double prime plus 3y prime minus y is equal to 4e to the t. Looking at this, we expect our solution is going to be e to the alpha t. We have our corresponding characteristic equation, r to the third minus 3r squared plus 3r minus 1 equals 0. If we assume we have some real roots, and we assume that they are of the form p over q, they're rational, then p must be a factor of minus 1, and q must be a factor of 1. So we have p is equal to plus or minus 1, and q is plus or minus 1. So we can plug in r equals 1, and we'll see we get 1 cubed minus 3, 1 squared plus 3 times 1 minus 1, and that does indeed equal 0. So this is one root. I can plug in and see if I have other real roots, but what I'm going to do instead is I'm going to take my r to the third minus 3r squared plus 3r minus 1, and I'm going to divide by r minus 1. So here I have an r squared, so that I can get rid of the r cubed term, and then minus r cubed, subtracting from what's above, I get minus 2r squared plus 3r. So to get rid of the minus 2r, I have to multiply this r by, to get rid of the minus 2r squared, I have to multiply this r by minus 2r. So I have my minus 2r squared plus 2r, and then finally I have r minus 1, so I have plus 1. So this here, our r squared minus 2r plus 1 factors into r minus 1 squared, so I have repeated roots, but I do have all real roots, right? This is a third order integral. I have one, I have one root here, and then I have r equals 1 repeated, well, I guess 3 times, twice here and once there. So the solution to my homogeneous equation, the general solution, is C1 e to the RT, that's 1t, plus C2 t times e to the t, plus C3 t squared e to the t. When I look at my general solution to the non-homogeneous equation, since my g of t is of the form e to the at, the polynomial, well, it's just a 4, so I'm going to have my, my constant coefficient a times, and then I want e to the alpha t, so alpha here is 1, so I have e to the t, but since that's here, I want this general solution, the particular solution y, to be linearly independent of this solution, the homogeneous solution. So I need to multiply by not just by t squared, but by t cubed. So y is going to be a t cubed e to the t. And remember, because of this footnote here, that y cannot be a e to the t, at e to the t, or at squared e to the t, because it needs to be linearly independent of yc. In other words, here, s is the smallest natural number that ensures no term in y, there's only one term, is a solution to the corresponding homogeneous equation. So here I've copied my solution to the homogeneous equation as well as the form of my particular solution, capital Y equals a t cubed e to the t. I can take the first derivative of y, the second derivative, and the third derivative, which is sort of long, but it combines so that there's only 4 terms at the end. Next then, I can plug in my y prime, y double prime, y triple prime into my differential equation. So I have y triple prime, which is here, and I went ahead and factored out my e to the t, which is in all of my terms. And then I have my y triple prime here, my 3y prime, double prime here, this is the double prime, and then my 3y prime is these two terms, and then last I have my minus y here. And it all combines out to get 6a e to the t, which is equal to my g of t, which is 4 e to the t, and that implies that a is equal to 2/3. Finally, I have my general solution. I have my general solution to the homogeneous equation, c1 e to the t plus c2 t e to the t plus c3 t squared e to the t, plus my particular solution to the homogeneous equation, which is 2/3 t cubed e to the t. My last example is y triple prime minus 4y prime is equal to t plus 3 cosine t plus e to the minus 2t. Here I have the characteristic equation r to the third minus 4r, which is equal to r times r squared minus 4, which is equal to r times r plus 2 times r minus 2 equals 0. So the solution to our homogeneous equation is c1 e to the 0 plus c2 e to the minus 2 plus c3 e to the 2t. Our g of t is the sum of 3 terms, so we're going to consider each term separately. So we'll start with g of t equals t. So here g of t is equal to t, and because t is just a polynomial of degree 1, so we're expecting our particular solution, capital Y, is going to be a naught t plus a1, and that's what we have here. But now we have to compare this to the solution to the homogeneous equation, and we see that this a1 is a multiple of the c1 e naught. This is just a constant, so we need these to be linearly independent. So what we need to do is multiply by a factor of t. So now we have a naught t squared and a1t. So now we are totally linearly independent of the terms of our homogeneous equation. So again, the extra factor of this t here is to keep the terms independent of this constant. So again, here I have this multiplied out. Y is equal to a naught t squared plus a1t. I can take y prime, y double prime, and y triple prime, and then I plug these into my differential equation, and I get my y triple prime minus 4y prime. So this is my 4y prime. And that's all equal to t. And solving this equation here, we get that a1 is equal to 0, and a naught is equal to minus 1/8. In other words, for t, my particular solution y is equal to minus 1/8 t squared. Looking at the next term of g of t, which is 3 cosine of t, since we're in this form now, we have the 3, so we do have a constant, our polynomial is just a constant, and we have cosine of t. So since we have this form here, there's no e to the it, cosine of t, so we have our constant, no e to the it, cosine of t plus a constant times sine of t. So here is our form of our solution for g of t equals 3 cosine of t. Now we can take y prime, y double prime, and y triple prime, and then plug it into our differential equation. And here we have our y triple prime minus our y prime over here. And that gives us 3 cosine of t, and we equal that to 3 cosine of t. Now that we have these two, this side of the equation, the left-hand side equal to this right-hand side, we could group our signs together, see that there's no signs here, and then solve, say that this is equal to 0. We could group our cosines together and say they should equal to 3 cosine of t. Another way of doing this is saying that this equation here should hold for any value of t, so I can just say for t equals 0, sine goes away, and I have cosine goes to 1. So I have minus c, my minus 4c is equal to 3. And for t equals pi over 2, our cosines go away and our sines become 1. I could have b times 1 plus 4b is equal to 0, since there's no cosine term. And that will give me c is equal to minus 3/5, b is equal to 0. So my y for my g of t equals 3 cosine of t is minus 3/5 sine of t. And now I'm going to add for my g of t, 3 cosine of t, that y is equal to minus 3/5 sine of t. So far I have 2, and I only have one more term to do. G of t is equal to e to the minus 2t. So for g of t equals e to the minus 2t, we have this form here. There's no polynomial unless you want to include 1. So we'll just put that one constant. And then we should have the form e to the at. So that would be e to the minus 2t. But this is already a solution of our non-homogeneous equation, so we need to add a factor, or a factor of t in here. So our y is equal to some constant, d, times t e to the minus 2t. And now we can take the first, second, and third derivative, plug into our differential equation. So we have our, and I factored out the e to the minus 2t since it is in all of our terms. Then I have my y triple prime, so it's my 12d minus 8dt. And then I have my minus 4y prime. So I have my minus 4d and my minus 8dt. And what that gives us is d is equal to 1/8. And here I'm going to add my last solution for g of t equals e to the minus 2t. That gives me 1/8 t e to the 2t. So these are my three solutions here. My minus 1/8 t squared, my minus 3/5 sine t, and my 1/8 t e to the minus 2t. Then finally, I can write my general solution. It's my homogeneous equation solution, c1 plus c2 e to the minus 2t plus c3 e to the 2t plus my 1/8 t squared minus my 3/5 sine of t plus my 1/8 t e to the minus 2t. So I know this is crowded, but I also crunched this solution all down on one page in case you wanted to see it that way. Maybe I should have done that for the other two, but here it is for this one. To review what we did in this video, we solved for higher order differential equations, non-homogeneous differential equations, using undetermined coefficient, and this was the table we used. So if we said if our g of t over here was of a polynomial form, then our particular solution to the non-homogeneous equation would also be a polynomial form. If it was a polynomial times e to the at, then our y of t would be a solution of polynomial e to the at. And last, if it was a polynomial e to the at times sine of beta t or times cosine of beta t, we would have the solution of a polynomial e to the at cosine of beta t plus a different polynomial e to the at sine of beta t. Then we also had this t to the s, and this was to ensure that no term in our y, in our particular solution, matches a solution to the corresponding homogeneous equation. So that's it for this video. Thank you for watching.